edition of the Cassandra Community Webinar Series. I am delighted to have with me today Boris Wolf from Comcast. And Boris is at the Comcast Silicon Valley Innovation Center. That's where Comcast works on exciting projects around the future of television. Boris is also going to be at the Cassandra Summit on June 11th and 12th, and will be presenting there. So if you haven't booked your tickets to that event, please make sure you do so. You can do so on the DataStax website. Before I hand over to Boris, just a couple of housekeeping items. Number one, we always get asked, when will the slides and video be available from the webinar? And we will aim to have that up tomorrow. We will email all of the registrants and attendees when those are available. Also, we will be taking questions during the presentation. So if you have a question, please use the Q&A panel in WebEx and type your question there. We will hold them until the end of the presentation. I will read them to Boris, and he will tackle as many as we can during that session. So a couple of key dates for you coming up as well. Please don't miss the next of the community webinars in the series, and I'll also just circle around on that at the end. So without further ado, I hand over to Boris Wolf. Thank you very much for joining us today, Boris.
And hello, everyone. I'm happy to be able to present here today. And yeah, let's jump right in here. So today I'm going to talk
Boris,
about—
just to let you know, we can hear you loudly and clearly.
Oh, that's perfect. Thank you. So today's topic is the Cloud Message Bus, CMB. This is a project that we've been working on at Comcast Silicon Valley for over a year now. And what it is, it's a general purpose message bus infrastructure that we implemented on top of Cassandra and Redis. And we've open sourced it by now. It's up on GitHub under Apache 2.0 license, so you can check it out there if you're interested. And so if you look a little bit closer, you see that CMB really consists of two separate services. One is CQS, which is a queuing service, and the other one is CNS, which is a topic-based pub/sub service. So the interesting thing here is both these services are fully API compatible with their Amazon counterparts, SQS and SNS, if you're familiar with them. And so if you are a user of SQS or SNS today, you could switch over to using CMB without having to change any of your code. So the compatibility goes so far that you can actually use the Amazon SDK to access our version of it, the CMB service. So today I will actually talk a little bit about the motivation behind why we did make that effort of implementing our own version of it, what our requirements were. And then I will go into a technical deep dive explaining the architecture and how we use Cassandra and Redis to our advantage. And then finally, I'll present a couple use cases, how we use this message bus in-house, and talk a little bit about what's next. So, but first the question, why did we build our own version of it? So obviously, Comcast is a large organization, so we have a lot of project teams in different locations, and many of them need some sort of message bus infrastructure. And what we find is that different teams use different technologies. So some end up using off-the-shelf open source solutions that are available out there, such as RabbitMQ. Others have been building their own custom solution tailored to their specific requirements. And what we are trying to do is really having one infrastructure that everybody can standardize on and share. So that's one reason. The other reason is we're operating a number of data centers across the country. So data center failover or data center outage is a possibility for us. And if that happens, if you imagine that service being deployed across all these data centers, we almost wanted to be agnostic to the fact that there are multiple data centers involved. So one example actually you could think of is if you just think of two data centers, you have clients in both data centers and they access the same queue by enqueuing and dequeuing messages. Ideally, you want messages to flow freely between data centers. But at the very least, if we have a data center outage, we want this to be, we want to have a smooth failover where there is no disruption in service and we don't lose any data, any messages in our queues. Then finally, another aspect is we need to scale. Obviously, you want to scale the traffic you pump through an individual queue, the throughput, but we also need to scale in a different dimension. So you could imagine use cases where we assign or dedicate one queue per set-top box that fits in customers' living rooms. So we have millions of customers, so that would translate to requiring to be able to create millions of queues. So we need to scale there in that respect as well. And then finally, we have pretty tight latency requirements. So at the beginning of this project, we sort of arbitrarily set this goal of 10 milliseconds response time for the 95th percentile. But what it really means is that even though we want to deploy this service across multiple data centers, for clients for this service should experience data center local response times. So we did evaluate a number of other options out there to use for this purpose, and we rejected every one of them for different reasons. And then finally, we arrived at the Amazon SQS and SNS services, and we really liked their API and how these services are designed. So to get a little bit of an understanding, just in case you're not familiar with SQS, I'm giving you the 60-second primer here of how SQS in Amazon works. They call it the simple queuing service. Everything is centered around guaranteed delivery there, and which is a key requirement for us as well, by the way. Like message loss is really not an option for us. Whereas messages being delivered in order, the service makes a best effort there, but there are no guarantees being made. So you could occasionally, happy day scenario, you will receive messages in order, but every once in a while you may see out of order delivery, and on the client side you would need to take care of that. Same goes for duplicates. We have guaranteed at least once delivery, but there is a possibility for duplicates, and again, the client needs to be able to handle that. Now, there are a few core APIs, very simple and straightforward. There is a send message call and a receive message call that you use to enqueue and dequeue messages, but then there is a delete message. So why do you need delete message? That's sort of like the Amazon twist here in this stack. So the way this works is basically the assumption is that you do not trust the message recipients, the clients that pop messages off the queue. So imagine you have multiple identical clients competing for messages from the same queue. Now, one client happens to pop off a message and then crashes before that client was able to actually adequately process and deal with that message. Now, if that happens, the message, basically when you receive the message off the queue, it will not actually be deleted off it, it just becomes invisible. And a timeout, a visibility timeout will be associated with it, which is by default 30 seconds. So if that client that popped off the message dies and never comes back and deletes the message to confirm that it actually processed it, it will reappear on the queue magically after 30 seconds for another client that has not crashed to pick it up and deal with that message. So that is sort of like in very brief terms, the core, the essence of that service. Guaranteed delivery, at least once delivery, and there's this sort of transaction that you pop off a message by receiving it, and then you need to come back a second time and delete it to actually confirm that you processed it. Now, again, question, so why did we develop our own version? Why did we clone the service? So yes, we do like the fact that it's guaranteed delivery. We like the simple standard API and the scalability of this. But I guess the biggest, like business concerns aside, the biggest technical reason to that didn't work for us using SQS is, first of all, latency, because by definition, everything you do in the Amazon cloud is a cross data center activity unless you sort of like deploy all your services in Amazon, which at least in the near term is not really an option for us. And then also the SQS service by Amazon has certain limitations in terms of message size. So message size is limited to 65 kilobytes, for instance. Certain timeouts, there's like a message retention period that cannot be extend more than, I believe, 10 days. And then finally, there you can schedule future dated messages. And again, in SQS, there's a limit of no more than 15 minutes into the future. So by implementing this stack on our own, all these limitations simply become properties in a numbers in a properties file for us that we can adjust to our own needs. So to summarize, what we actually set out to do a year ago was build a horizontally scalable queuing service on top of Cassandra and Redis, which is API compatible with Amazon SQS and SNS, I should say. So a little bit about why did we choose Cassandra and Redis. So Cassandra we chose basically for its cross-data center persistence and replication ability. It comes with that essentially out of the box, and we don't have to worry much about it, and it was a key requirement for us. And we know from experience in-house and from literature that it's proven to scale massively horizontally. And then Redis, at first we implemented this purely on Cassandra, and then a little bit later we did some refactoring. We brought Redis into the picture simply to meet our tight latency requirements. And also, as you will see, Redis is not just a simple cache like memcached, for instance, but it also provides a rich set of data structures such as lists and so forth. And we use that to our advantage to help with the best effort ordering of messages and to handle the visibility timeout mechanism that I was just describing when I explained the delete message API of the SQS stack. So at first, before I go into the entire architecture that shows how Cassandra and Redis play together and make the queuing service happen, I want to spend a little bit of time talking about Cassandra data modeling here. So our schema has a number of column families that store all kinds of things like user metadata, queue and topic metadata, but really the key problem that we faced was the key data structure is how do we represent messages that are currently in a queue. And we went through an iterative design process coming up with different options on how to design this, and I just want to quickly walk you through what we did here and what design we came up with ultimately and what were kind of like some steps along the way. So if you are, so this here is supposed to be a representation of that column family that represents the messages that are stored in a queue. And if you are coming from a relational database background, as we were at the time, you may be tempted to say, okay, I want to store all the messages that are associated with one queue in a single column. So if you do that, basically what you're saying is, so you could, the row key could be, for instance, the timestamp when the message was received, and then you have a single static predefined column called message body here in this diagram. And then as messages come in, you have message 1, 2, 3, 4, 5, 6. They come in with their timestamps. The timestamps will be the row key, and the messages will be values in that message body column. Now, the problem with that is that what kind of questions do you want to ask the queue? You probably want to look at the head of the queue and the tail of the queue. Maybe you want to squeeze in future dated messages somewhere in between. And the problem is, out of the box, Cassandra doesn't allow you to do like range slice queries that you would need to be able to do to figure that out. So basically, unless this would only work if instead of the default random partitioner, you would use the order preserving partitioner, which sort of like preserves the order of rows as they are put into nodes on the ring. But basically everybody we talked to who knows Cassandra better than we did at the time was sort of advising against it and said order preserving partitioner have some disadvantages, and you should really only use them if you don't have any other options. So we were like, okay, that was our first design. Why don't we do it another way around? So here we are storing all the messages that are in a queue in a single row. So again, we have timestamps. and then message bodies that are associated with that. But now you find all these messages in a single row, and the row key is the queue ID, in this case, Q123 as an example. So now you take advantage of a very neat feature of Cassandra, which is that it naturally sorts all the columns in a row. So in this case, we chose timestamps. So we will see the timestamps. We will see all the messages nicely sorted in chronological order. And you now can do column slice queries that allow you to access the head and the tail of the queue and do all these kinds of operations that are important to us. Now, there's one problem here with this design, and that is that in Cassandra, if you this row, obviously, if you have a very busy queue, could get pretty wide. So you will end up having like a very wide row, and all the messages that are in one row will always map to one node in the Cassandra ring. So that could be a problem or a potential bottleneck. As you have a very hot queue, you would like route all the traffic for that queue through that one single node. And also keep in mind here that we are implementing a message queue on Cassandra. Is not really the typical use case. In the literature, there are a lot of examples of using Cassandra for like sort of like write-heavy applications, time series data such as logging, where you sort of like keep writing a lot of data in some sequential order, and every once in a while you read and you rarely delete. But in our case, this is different. A queue has almost an equal amount of reads, writes, and deletes. So we have a lot of churn here, and that will also produce a lot of tombstones, and we need to control that as well. So we figured, in particular, in our case, having all these messages for one queue and one row would be too limiting. So what we ended up doing is sort of like a hybrid approach where we sort of like shard now all the messages for a queue across a number of rows. And in this case, by default, we shard across 100 rows, but you could change that per queue to a different number as well. But here in this example, again, you have this queue with the ID 123, and then you have shards that are indexed from 0 through 99. So as you can see, the messages, as messages come in, they are written into random shards of that queue, but they still sort of preserve that ordering because we're using timestamps as column names. And actually, I'm introducing another thing here in this slide. Instead of timestamps, you should probably use time UUIDs. What this essentially is, it's still timestamps, but it's sort of like a composite key that adds some entropy to it. So if you had like two clients that are sending messages at the same time, at the same timestamp, those messages would not override each other, but these time UUIDs are globally unique and sort of guarantee you that you don't have that situation where you would see collisions if there's a lot of traffic going across that queue. So again, by doing this sharding across 100 rows, we now have the advantage that we're automatically sharding the traffic for a queue across up to 100 nodes in a Cassandra ring, if your ring is even that big. But the point here is that we are using multiple nodes in the ring to deal with the queue's traffic, and that is exactly what we want. Now, the only problem that we are facing here is now, I mentioned we are sending messages into random shards, and we are also reading from random shards. So that could mean in this example here, if you issued a read request and you happen to read from shard 00, you will read message 1. But because it's random, you could also end up reading from row 99, and you would read message 3 before message 1. However, you would never read message 6 before you read message 1, because that is in the same row, 00, and you would sort of like get message 1 first. So globally, we still have good ordering of messages, but locally, any two given reads, consecutive reads, might still have some probability for out-of-order delivery, which is okay. I mean, that's not against the contract, but again, we are trying to make a best effort here. And you will see that is sort of where Redis comes into the picture, which helps us in straightening out that ordering problem. But at least from a Cassandra perspective, this design here, sharding messages across multiple rows and using time UUIDs as column names, was the design we ultimately chose, and that has been working well for us. So to explain how Redis works, here I will use a quick data flow example. I will use one queue and send 3 messages onto that queue, messages 1, 2, 3 in that order. and then I will receive a message, and of course that will be message 1 because that was the first one I sent, and then finally I will delete that message to really pop it off the queue. So here you see in the upper left, that's our web service endpoint, a simple REST API endpoint. We host that on Jetty, basically. In the lower left of that diagram, you see the Cassandra column family that I just explained that stores queue messages across a number of rows. And then on the right, you see Redis. And I mentioned before, Redis provides different types of data structures. So we have a list here and then hash tables and so forth. And you will see how these things work together. So I send in a first message. The message will be written on a random shard in that Cassandra column family, and we put the message ID onto a list in Redis. And we have one list in Redis per queue. And the message ID is an aggregate, a composite really, of the row key and the column name. So we have the full information we need to pinpoint the message in Cassandra, the queue ID, the shard index, and the time UUID. Then we send 2 more messages, and you can see they trickle in. They go into different shards or random shards in Cassandra, but they all go into the same list in Redis, and they are nicely ordered because essentially that list is an in-memory queue, if you will. So that's what helps us doing the sorting. So now when I receive a message, I pop that message off that list in Redis. And notice what happens in Cassandra. Essentially, nothing. We don't delete anything. We don't write anything. We just don't do anything. The entire dealing with the visibility timeout happens in Redis, which saves us a delete and a write operation in Cassandra, which helps us, again, controlling the churn that we create there. Now, the visibility timeout is handled in this hash table that is labeled automatic VTO. So you see here, as the message was popped off that Redis list, as the message ID was popped off that Redis list, it was placed into that hash table. So the message key here is the key in that hash table, and the value is actually a timestamp, which is dated 30 seconds into the future because 30 seconds is the default timeout, visibility timeout for messages. So there's a background process that keeps checking that hash table if messages have to be made revisible. But in this scenario, we are assuming it's the happy day scenario. The client processes that message 1 in the correct way and comes back and deletes the message. And that is then finally what removes it from that Redis hash table. And then finally, we do a delete from Cassandra, which essentially removes that message from the Cassandra column family. So I know this was really quick and brief, but essentially this is really the core of how enqueuing and dequeuing works together with Cassandra and Redis. Now, a quick architecture recap. Cassandra is our persistence layer. Messages, as I mentioned, are sharded across 100 rows, and we mainly do that to distribute the queue traffic among Cassandra nodes in the ring. Redis was introduced as a caching layer to meet latency requirements, but then we realized that it also lends itself to improving the orderly delivery of messages, and we use it to handle all of the message visibility, all of the business that happens between receiving and deleting a message. Cassandra doesn't have to be involved in that. So what are some of the key features that we used from Cassandra that made Cassandra so appealing to us? Obviously, the main reason, the driver, was that Cassandra has this ability to replicate data across data centers sort of by default. You don't have to do much or configure much to make that happen. And the other thing that was appealing to us is this aspect of tunable consistency. So all the reads and writes we are doing, we are choosing local quorum reads and local quorum writes. And what that means is the ring in your local data center, we are accepting a read or a write operation as successful as soon as a majority of the replicas in your local data center have confirmed the operation. We know that eventually all this data will also travel to the ring as it spans multiple data centers into other data centers. but we are okay with the fact that there is a short period of time where we cannot be sure that the data has already arrived there. Now, you could turn that consistency level up. You could turn it to like either all or all quorum all, or you could turn it down to just one or any. And basically what you are doing then is you are sort of like trading response time for guarantee in terms of whether your data is actually persisted or not. But it seems local quorum reads are a really good balance between response time, latency, and availability, basically. So we ended up doing that, but you could change that if you wanted to. The other reason we chose Cassandra is because we need to scale to millions of queues, as I mentioned before, and we know Cassandra has the ability to scale as far as your resources let you, basically. But then once you get into the nitty-gritty detail of actually implementing it, there are a number of really neat features that make Cassandra work very well for us. For instance, I mentioned there is a message retention period. If nobody picks up a message of a queue, by default, after 4 days, this message will just disappear. And the way we implemented that is by putting a TTL, a time to live, of 4 days on every column value that represents a message in a queue. So we don't really have to do anything. It's simply the Cassandra TTL that will ensure that we guarantee that this message retention period is met. So again, we came to this from a relational database background, and the team that worked on that didn't really have any Cassandra experience coming into this. And so here are a couple quick lessons learned for us, like transitioning from relational database to the NoSQL world. So a lot of introductory articles sort of like make this analogy saying like, oh, you can think of a column family as a table, right? Because you have columns and rows and so forth. But we found that this analogy is really not very helpful. Rather, so I'm a Java person, so I wrote some Java syntax here. What my understanding of a column family is, rather you should think of it as a hash map that maps row keys to tree maps. And those tree maps in turn map column keys to column values. And the only reason I'm choosing tree map here is because that's sort of like Java talk for saying, I want a map that sorts by the key. So you have the sorting aspect here that columns are sorted, or column values are sorted by column keys, whereas the rows are not necessarily sorted by a row key unless you choose the order preserving partitioner. So if you look at it this way, all of these no's that come with NoSQL sort of like start to make a lot of sense, right? So there's no need to specify column names in advance. You don't need like a static schema that you would sort of like need in a relational database. And this is exactly what allows you to have like wide rows, valueless columns, composite keys. All those things then start to make sense. And furthermore, you have no unique constraints, no foreign keys, which really means you have no complex queries, right? You cannot really write complex queries. So the answer is really identify like what is really the key data structure in your system and design your schema around your queries. And that is sort of like the example that I was making earlier. Like the key data structure for us was how do we store messages in a queue, and what are the queries that we're going to be asking, and so then come up with a schema that lends itself to asking these questions. So I think the only thing we really found that reminded us of relational world there are indexes, right? You have the primary index on the row key, and you can define secondary indexes on predefined columns, and by all means use those to make your queries more efficient where it makes sense. But yeah, I just thought that was interesting. Quick words on scalability and availability. So the key operations on the queue, send, receive, and delete, they all scale with the Cassandra ring and the API web service endpoints, which are stateless, and of course Redis shards. So one thing I didn't mention, by the way, is we are using sharded Redis. And the sharding key is the QID. All operations are constant time operations, so they scale well. And so I guess the only potential bottleneck is really introduced by Redis, not by Cassandra, in the sense that since we use the queue ID as the key for sharding over Redis, like all the traffic for one queue will always go over a single Redis shard. But in practice, Redis performs really well. That hasn't really been an issue for us. Availability, we're sort of like banking on the availability of Cassandra here, and we feel that's a pretty safe bet. And the other interesting aspect is that the service functions without Redis. If Redis goes down, the service is still available, there's no message loss. The only thing you would observe is degraded performance, and then of course, because we lose the management of visibility timeout, you will see a lot of duplicates, but the service is still available, and you have still the property of guaranteed delivery. So here, to finish up with CQS, I have a quick example. Imagine this service distributed in two data centers, DC1 and DC2. So you have two completely identical deployments here behind a global load balancer that will then route traffic. In this case, data center 1 is the currently active data center. So all traffic that comes from clients requesting operations on queues will be routed to the local load balancer in data center 1. That will then round robin across the service endpoints, and those will then access the Cassandra ring and the Redis shards to do their work. Now, the one thing you notice here is the component that spans across data centers is the Cassandra ring. This is an 8-node ring, 4 nodes in data center 1, 4 nodes in data center 2. And as I said before, all our operations are local quorum reads and writes, so they will be confirmed in that data center 1's ring, but then eventually they will also spill over to data center 2. So now if you want to think about a failover scenario, if data center 1 goes down, the global load balancer will detect that because it's performing occasionally, it performs health checks. And then from one moment to the next, it will reroute all traffic, all CQS traffic from data center 1 to data center 2. And that's fine because all the data, all the messages in the queues are readily available in the Cassandra ring and data center 2 as well, which is really nice. The only problem is that, of course, again, Redis, the Redis shards in data center 2 are completely unaware of all queues and all messages. They have just been sitting there in standby. And again, we have background processes that sort of like kick in this case. If there are cache misses, there will be background processes that start heating up these caches, and that will take, depending on how much data you have in the system, a few seconds or a couple minutes. But after a while, the service will be fully available with the same performance again as before. And again, you don't lose any messages, which is really the key feature here around guaranteed at least once delivery. Now, and with that, that was sort of like the part of the talk that deals with the queuing part of the service, CQS. Now, I'm spending a little bit of time on SNS and our version CNS, the pub sub service. We don't really have the time to go into the same level of detail here, but I just want to briefly point out a few things about the CNS service. So it's a topic-based publish-subscribe service. The supported protocols for subscribers are primarily HTTP, so usually you do HTTP posts to these subscribed endpoints that subscribe to a topic, but you can also subscribe queues as endpoints. So you can publish into a CQS queue or even into an Amazon SQS queue because they are API compatible, right? So again, there are a few core APIs. Primarily, we just have to deal with creating a topic, then you subscribe endpoints to that topic, and then finally you publish messages on a topic, which will then result in sending out those messages to all subscribers. That's really the core of it. And I will, again, explain how this works or how we implemented it by using a very simple data flow example. And in this case, I'm just making one call, which is we're assuming the topic is already created, the subscribers are already subscribed, and we just publish a message, message 1. And the topic we're dealing with here is topic T, and we're assuming there are 4 subscribers. There's S1 and S2, which are HTTP subscribers, and then there's S5 and S6, which are CQS queues as subscribers. So again, I have a little illustration here. You see how the publish message call comes in at the web service endpoint on the left. And so just to clarify here, the 2 green boxes are what you would see as a user. You see the web service endpoint that you can hit with API calls to SNS, to CNS, where you publish messages or subscribe or unsubscribe. And of course, you, as the owner of the subscribers, you also see the endpoints where messages arrive. What you see in the middle, the blue box, is really the internals of how we implement the CNS service, and you as a user never see that from the outside. I'm just explaining the architecture here and how we implement the service. And the thing I want to point out here is that we use CQS queues to implement the CNS service, and we use these queues to distribute the burden of fanning out to potentially a large number of subscribers. Like if you think you have like a topic with 1,000 subscribers or so, that is a lot, right? If you were to do that with a single publisher, that's a problem. And we use CQS queues to sort of like distribute the workload here and make latency manageable. So when you publish a message, what will happen is we will write a message into the queue that is named publish job queue here. And all this message contains is the message body itself and the topic ID that the message is destined for. And then we'll have a background process that will read from that queue, analyze which topic the message is for, and inflate it with all the subscribers to that topic, and actually chunk it up in sizable amounts of work. So if you, for instance, have, like, say, 1,000 subscribers, we would chunk it up into 10 subtasks of 100 subscribers each. So in this example, we only have 4 subscribers, and just to illustrate that here, I'm chunking it up into 2 messages, and those contain the message that is to be published and the subscribers that the work is destined for. And then there is a different set of workers in the background that pops messages off that second CQS queue, that endpoint publish queue, and does the actual fan out to the subscribers, and the message arrives on those 4 endpoints. And that's really the flow. So again, publish, go into the first queue, inflate it with all the subscribers and chunk it up, and then fan it out. That's the workflow here. Now the interesting thing, like it kind of like works well for us using CQS queues as the underlying mechanism here, because messages are preserved when even when those background workers that do all the fanning out are down or overloaded, so nothing gets lost. Again, we have guaranteed delivery because we are building on that feature of the CQS queue. And also the visibility timeout of the CQS queue, the built-in visibility timeout, takes care of the guaranteed delivery aspect as well. Like if one of those background processes dies while it is publishing to an endpoint, before it gets to delete the message from that internal queue, it will reappear on the queue and a different worker will take care of it. So that works very well for us. So again, I was brief here. There's a lot more detail, but just as a high-level overview, that was my quick intro into the CNS publish subscribe service. Comparison of our implementation with the Amazon SQS and SNS. Our goal is full API compatibility, and we are pretty much there. We are implementing all APIs. Pretty much all parameters are supported. And you can even use the Amazon Java SDK and other language bindings to access the service. There are some things we do not implement yet, like one example is digital signatures, the latest version of it at least, version 4, we don't support that. Version 1 and 2 are okay, and we're working on catching up there as well. And, but really there are not that many limitations, or SMS endpoints, we don't support that right now because we didn't really have a need for it. But again, I mean, we could add all these things if there was a need for that. However, more significantly, we do provide a number of enhancements, most notably the fact that you can create an unlimited number of queues, topics, and subscriptions in our system. Whereas I believe in SNS, in Amazon, you're limited to like 100 topics per user and similar restrictions. And you can adjust all these other parameters such as message size and timeout periods and so forth. So with that, I'm now transitioning to an actual use case, what we are using this for in-house. And this is a use case for the CNS PubSub service. So what you see here is a screenshot of our X1 set-top box that we are now rolling out to customers. And so what you see here is what we call the sports app. So in the left where you see travel channel, that would be the area where you typically watch the TV channel you're currently watching. but then you can open apps. And in this case, we would call that an L view because you have an app that occupies part of the screen, and then on the left you can actually see the program. So this sports app allows you to follow live sports events. We cover NHL, NBA, and a couple other leagues. And you can see sort of like what games are currently on, what is the current score. You can go into some sort of detailed screen that shows you the detailed score, the last play event, and other statistics about the game. And if you stay on that screen, it will update as the game progresses and events come in. And in the back end, we drive that with by using a CNS topic, a sports topic that sort of like publishes, sends out these game event notifications to all sports apps that are currently running on customer set-top boxes. So here, this is a look at the back end, right? So we are looking at a single endpoint receiving events, sports events. I took this scan here during a month in December last year, I believe. This is roughly a month's worth of data, and you see these little clusters of messages where, typically it's around like 10 messages a second or so for a certain period of time. Those are times when evenings or afternoons when games are on. And then you see some times where there's an exceptional high amount of messages, like maybe 60 or 70 per second. That was like probably a game night where a lot of different leagues like NFL and NBA maybe were, or a number of other leagues were having a lot of games at the same time. So again, so here, this is like one nice use case we find for our CNS pub sub service. This is a second use case. Yeah, this diagram is not very pretty, but imagine the boxes on the right were set-top boxes, X1 set-top boxes in customers' living rooms. And the use case here would be, so for instance, the emergency alert system, right? Say there was like an earthquake somewhere in the country and you wanted an emergency alert to pop up on everybody's TV screen, basically, either by zip code or by state or even nationwide. So this would be a typical use case, again, for a CNS publish-subscribe topic, right? You have a topic for the emergency alert, and you would sort of want to fan out that alert to all set-top boxes. But the problem is, if you use the standard mechanism of pushing HTTP posts, you typically cannot really reach those set-top boxes. You cannot really reach a port on these set-top boxes because typically all of them sit behind some sort of firewall. So this is an example, a good use case if you were wondering why would I ever want to subscribe a queue rather than just a straight HTTP endpoint. So in this case, in this example here, we have one dedicated queue per set-top box in our data center essentially. And we are publishing, the topic publishes messages into that queue, and then the set-top box can go out and pull data from that queue. So by doing that, we can sort of like circumvent that problem of having a firewall in the middle. So that is a nice use case for seeing how CNS and CQS can play well together in a use case. And I just thought that was a nice example. So that's pretty much what I have, like just a couple words here moving forward. As I mentioned, we have it open sourced under Apache 2.0. It's on GitHub, so go there, check it out. Of course, we're still, since we decided to sort of like clone the SNS and SQS APIs, we're sort of like following their stacks as they evolve because they change their API as well, obviously, as time moves on. We're currently doing a significant amount of load and stress testing, I will do a talk at the Cassandra Summit in June around the same topic, and I'm planning to present some more data really around like really hard numbers around how the system scales. We are currently working on simplifying the deployment and the scaling up of the system to make it actually more easy to install it and get going with it. And we're looking at our first production deployments that are currently still isolated by application, but of course the long-term goal would be to have like sort of like a CQS or CNS as a service that could be shared by many users. And then finally, as CMB is a re-implementation of an Amazon Web Service API, it sort of like makes sense to think of OpenStack And we are currently figuring out where we could fit in the OpenStack world or how we could integrate with OpenStack. So that's what we're currently doing. And with that, I thank you very much for your attention. And here's our GitHub link. We also have a Google Groups forum where you can sign up and ask questions. And then finally, there's my email. You can feel free to send me an email directly if you have any specific questions. So I think at this point, I would be ready to take some questions.
Thank you very much indeed, Boris, for that. And just a reminder, if you would like to ask Boris a question, please use the Q&A or chat tab on inside a WebEx, and I will go through those and ask Boris. So just a reminder, because we're getting a couple more questions for people that joined late. They are asking about the recording and the slides, and a couple of people want to share with others on their team. We will have a recording of today's presentation up on our community website, planetcassandra.org, probably by end of business tomorrow, and also the slides available. We will send an email to all the participants and all the registrants when that is available. So do not fret if you joined late and missed a little bit of Boris's introduction. Also, Boris will be at the San Francisco Apache Cassandra Summit, which is on June 11th and 12th. Giving a more detailed deep dive talk from the one he did today, and by then sharing some more data. That is at Fort Mason, and if you are looking at your screen right now, SF Summit 25 will get you 25% off of the ticket price. We have a great event planned. So Boris from Saku, do you use equal number of rows and Cassandra nodes in multi-row queue setup?
Okay, so if I understand the question correctly, the question is whether we use the same number of shards for each queue. And in the beginning, that is what we did indeed. We had it like fixed at 100 shards per queue. But we have recently changed that and opened that up a little bit so that when we essentially made that a queue attribute now, which is obviously not a queue attribute that you could set like in Amazon, right? Because it's our own implementation, but still you can actually send that through the Amazon SDK regardless. So by doing that, you can now define as many shards as you like on a per queue basis, either when you create the queue or when you change the queue attributes. So by doing so, you could have a queue with as little as 1 shard, and you would already get like perfect ordering out of Cassandra without even involving Redis if you have a queue that doesn't see a lot of traffic. Or you could increase that number of shards to anything between 1 and 100. Going beyond 100 probably doesn't usually make sense. But yes, so the answer is if you just go with the defaults, you will end up with 100 shards, but you can change that to a different number if you need.
Great, thank you, Boris. Questions coming thick and fast now. We'll get through as many as we can. Giancarlo asks about data modeling. Did you use CQL2 or CQL3 to model data?
So we are currently when we started out, I think CQL3 wasn't quite ready yet. So we did use some CQL, and we still do that today. But for the most part, so by the way, I mean this is implemented in Java, and we are using the Hector library. So for the most part, we get away with mutators and slice queries and so forth. So we don't really use a whole lot of CQL, but as far as it goes, there's a couple of places where we use CQL and not CQL3.
Okay, thanks. And yes, CQL3 has been available since January with the 1.2 release.
Mm-hmm. Right.
Okay, so next question from Patrick. In case of a Redis failure, how do you transition the client from Redis to Cassandra?
So you don't really need to transition anything to do that, because essentially it's the implementation. The implementation of that sits in the web service endpoint, which is really a Java servlet in a Jetty or a Tomcat app server. So when you do your request to like receive a message or to send a message, the implementation of those API calls will do the entire job of using Hector to go to Cassandra and using the actually Redis library, by the way, to go to Redis. And the code is written in a way that a Redis failure will not really matter, right? You will still get the service response for a receive, send, or delete call, and internally we log the fact that Redis is unavailable, and that we escalate that to make sure that somebody takes care of bringing Redis back up and so forth. But to the user, it's really transparent, and again, there's no real operational activity that has to take place to sort of like transition from back and forth between Redis and Cassandra. It's built into the code, really.
Okay, thank you very much indeed. Let's have a look here. I'm not quite sure exactly what this one is, but you will know it, Boris. What will you do differently to guarantee FIFO-ness? And that's from Thomas. And he then asks a bit of a follow-up clarification, or if you need to support the orderly message, e.g. need to guarantee the timestamp order.
Right. So this question is around the FIFO-ness or the message order, right? So what if your application really needs orderly delivery? I guess that's what the question is. So, well, one thing I just mentioned in an earlier question was that so you have the ability to define the number of shards for that you use in the Cassandra column family, and if you change that to 1, right, you will sort of have perfect order of your messages, no matter what, with or without Redis. And also, as long as Redis is around, and as long as you don't do a data center failover, it's Redis that will guarantee the orderly delivery, right? So you will get messages in order. It's just you cannot. That's the happy day scenario, right? So there's still that potential for occasional out of order deliveries, and yeah, I mean that was sort of like our decision, like that we say we want guaranteed delivery and availability and robustness. Those things are more important to us than handing like a duplicate-free and perfect order messages to the client. So yes, that is not really the classic understanding of what a message queue's contract should be, but in practice, it's fine. And also, I mean, if you really need order delivery, then we're saying, well, that's the client's responsibility to ensure that you don't consume duplicates if that's an issue, and you order your messages in case you get some out of order delivery. Yeah. So I guess the short answer is, right now that is the design, and it wouldn't be easy to change that to sort of like guarantee those things, the order and the singleness of messages as well.
Great, thank you. So still coming thick and fast. Let's see how many we can get through. Shashank asks, was Kafka RabbitMQ considered for evaluation? If so, what are its disadvantages/advantages? Before you answer, Boris, Shashank, feel free to email me, christian@datastacks.com. We have another company, Career Builder, that is using RabbitMQ, and I know of another company, Health Market Sciences, using Kafka, that I'd be more than happy to give you an introduction to. But Boris, did you look at anything else like that?
So yes, we did evaluate a number of other options. We didn't look at Kafka, I believe, but we did look at RabbitMQ, we looked at ActiveMQ, we looked at ZeroMQ, and a couple others as well. So I think the issue with RabbitMQ was that we had, well, I guess two things. Well, first of all, we had trouble generating like hundreds of thousands or millions of queues with RabbitMQ, at least out of the box and at the time that we looked at that. So, I mean, that may have changed, and we may not have had the appropriate setup for that, but it was one of our key requirements to be able to sort of like at ease scale, to hundreds of thousands or millions of queues and topics and thousands of subscribers. And that seemed a little bit challenging in RabbitMQ. And then the other thing is, Rabbit is implemented in Erlang, right? And which is a great language, but at the same time, it's a little bit awkward and new. And I guess our concern was more around the Erlang runtime environment, the virtual machine, whether it's stable enough, or we couldn't fully understand how the garbage collector works. And we just felt, I mean, we're traditionally, we have been doing Java development, and so we felt a little bit uneasy about bringing the Erlang technology into that picture. But having said that, I mean, if you don't need millions of queues, and if you're not worried about Erlang, then I think RabbitMQ would be a fine choice as well.
Marshall asks, what magnitude of hardware for what throughput per second, if you could use round numbers?
Yeah, well, that is sort of like a difficult to answer question. I mean, we know that, I mean, in theory, you can do like, with average server hardware, you can probably do like 10,000 operations per second through a Cassandra node or through a Redis shard, maybe like 1,000 of operations through an API server. So you can sort of like do the math here and sort of like come up with the numbers, what you need in terms of ring size and how many API servers you need. I mean, the whole goal of it is horizontal scalability. So in theory, you can scale to whatever you need. But again, having said that, we are really in the middle right now of running these types of load tests, and we're assembling the numbers, and we will hopefully be able to present some nice diagrams at the Cassandra Summit coming up. So I can't really give you a much preciser answer than that, but yeah, that's it.
Okay, and thank you so much, by the way, for answering all these questions. Do you have, Sudhir asks, do you have a use case where the publisher is notified if the message times out and is cleared from the Cassandra row based on its functionality?
Yeah, so we don't have a use case for that, and it's not a feature that we have implemented right now or even on our roadmap for that matter. And I think for the most part, I mean, really our goal is retaining API compatibility and feature compatibility with Amazon. So we pretty much do what Amazon does. So for instance, last fall, Amazon introduced long polling for queues, because reading from queues is really not a push thing, but a poll thing, right? So they introduced long polling for that, and we followed step here and implemented that as well. But other features, like usually when people come to us and say like, oh, hey, can I have this feature? If it's not in the Amazon stack, we would typically say no. One of the rare exceptions was the sharding that we made available as a queue attribute, but that's sort of like an exception.
Okay, this is going to be the last one. Why, Doug Thompson asks, why active, passive, hot instead of active?
Yes, that's an excellent question. So I think so. We obviously we chose Cassandra to be able to do active, hot kind of queues, and that is still the goal here. The only reason that we cannot do it right now, the only reason that we have one active data center and one in standby, and then we sail over, is really the Redis cache right now. And there is, I understand there's a project going on in the Redis community to sort of like have, I believe it's called clustered Redis, but again, that's not quite ready yet. So without that, unless we sort of like invent our own solution for that, we have some issues with Redis to truly do the active queues. But I mean, we have again, we have some ideas on how we can get around that, and we have a roadmap for that, but not a set in stone date yet when this will be available. But certainly, I mean, Cassandra does not stand in the way of that, and that's the reason we chose Cassandra. And we are working on figuring out the problems that prevent us from doing active right now, and we'll do so hopefully in the near future.
Okay, well, thank you everyone for joining me today. Do not miss next, they're coming thick and fast. So next Thursday, we have an introduction to Apache Cassandra 1.2. Aaron Morton, a Cassandra committer, prominent member of the community, will be presenting. May 2nd, data modeling, hot topic in Cassandra. The data model is dead. Long live the data model. That is Patrick McFadden, and then he'll be doing on May 16th a follow-up to that, going deeper into data modeling. Boris, thank you so much. We really appreciate your spending the time. Looking forward to seeing you at the Cassandra Summit in June.
I'm looking forward to it too. Thank you so much.
Okay, thanks everyone. Bye-bye.
Bye.